Welcome to July 23rd's LeetCode Challenge, Binary Tree Pruning. Given the root of a binary tree, return the same tree where every subtree of the given tree not containing a 1 has been removed. The subtree of a node is a node plus every node that is descendant of a node. It's basically 5 nodes in a sentence there. So we're given this binary tree here, root here, we have 1 null 0, 0, 1, and we want to prune all the subtrees that have a 0 in it. So basically every kind of leaf that has a 0 in it, we want to prune that. Once that's pruned, if the leaf itself is a 0, that's not connected to a 1, that's also pruned as well. So giving example 1, this leaf node 0 is pruned, therefore we have to output basically 1, null, 0, null, 1. Likewise, same here. We have the tree root, a tree array here where we have basically right here, and then we want to prune all the leaf nodes that are 0. Once we do that, we also know that this is a leaf node afterwards, and that's 0, so we want to prune that, and therefore we get the output same as above. Let's see, likewise, prune the leaf node 0, and then there's nothing attached to it that's also a leaf node that's 0, therefore we just return the output. Constraints, number of nodes is between 1 to 200, and node value is either 1 or 0. So basically, we want to prune all the 0 leaf nodes, and then we look at our tree again. If there's another 0 leaf node, we prune those, and we keep on pruning until there's no more 0 leaf nodes, ideally. All right, let's how I'm going to approach this. For the tree problems, we can usually do it using a clean recursion, which is what I'm going to do. My idea is probably to recursively traverse through the nodes of the binary tree. If the current node subtree contains a 1, so if and only if the root val is equal to 1, or the left subtree or contains a 1, or the right subtree contains a 1, then we return the root, else return null. And then we just set the root left equal to null if the left subtree does not contain a 1. Otherwise, we set the root left as it is. Do the same thing to the right, set it to null if it doesn't contain a 1, or leave it as it is, as a 1, original node. And then yeah, that's pretty much it. Let's see how we're going to go about doing that. So I kind of walked through the idea. Now let's try to do it. So if the root itself does not exist, then a root equals none. Then what we want to do is return none, a root, because it's empty. So we just return this, it's the base case. Next thing you want to do is recursively call update our left root node, our root left. So we're gonna root.left is gonna be reassigned to self.prune tree. So it's a recursive call to itself on root.left. So this is ideally what I want to do is set the new left node. And likewise, you can do the same thing to the right. Self.prune tree root.right. So now that we have already set up 2 new root nodes, this is like setting up the new left node and the new right node, root node. Then what we want to do is find whether it's equal to none or equal to 1. So what do we want to do? So we want to check if the current subtree contains a 1 or not. So how do we do that? So if root.left is not equal to none, so it's not empty or not 0, or the root, I'm going to check both at the same time, right is not equal to none, then we want to do is find, or we want to find if root.val is equal to 1 as well. So we're checking if the current subtree contains a 1 or not. Then we want to do is return root, because those are the cases that we leave alone. Otherwise, we want to return none. Return none if the Let me see. Yeah, if this is not the case above. Alright, let me have my indentation correct. Yep, seems good. Let's run it. Oh, if root is equals none. Alright, looks similar. Accepted. Awesome. So this is actually, let me see. This is a depth first search post order depth first search. Yeah, that's what we're doing actually. That's our approach. Let's see. Time complexity would be big O of n, where n is the number of nodes in the binary tree, and space is big O of the height. Yeah, big O of h, the height of the tree, of the binary tree. So how many node layers, how many node heights it has. Like for instance, this one has 1, 2, 3, 4. Therefore, so yeah, the height of the node, the height of the binary tree, because it causes the depth of the recursion stack. So how many times you do the recursive step is the big O, the space complexity. All right, that's it. Have a great day.